Let's get it. I worked another problem, so um, they helped me with my PE. Hopefully, I'm gonna take it maybe sometime next year, whatever. So, so it says a 750 cubic meter tank containing wastewater flows through a 150 millimeter steel pipe. The pipe is 1,000 meter long that ends 15 meters below the bottom of the tank. The liquid depth of the tank is 3.5 meters. What is the discharge rate? All right. So let me bring up my solution here. Yep. Yes, sir. All right. Yeah, don't y'all just love my drawings? Huh? Man, I knew somebody uh, when I was in school that can just draw like like a pure artist. But his sketches was like just 3 dimensional and everything. I'm like, okay, all right, dude, it really ain't that serious. But all right. So I wrote the volume of the tank, and then I'm gonna assume entrance and exit losses. So um, hope you got something in your fluid books, to calculate those. But I'll show them on here, whatever. Hopefully, ours look the same. All right. So, all right, got all that. The sketch, diameter, change that to meters, and then I calculate the area of the pipe, which give me that number. And so the density of that liquid, I just assume it's the density of water, um, basically. Um, Wastewater uh, can just be very dilute. Um, um, yeah, just very dilute water, really. Well, very dilute or little diluted. I think it's little diluted water. It's close to purity to water. So, um, yeah. And so I did a mechanical energy balance. We know it's basically gravity uh, is the main component pushing that water down. Our point's gonna be point one, surface of the tank. Point two, the discharge. We know that the velocity at point one at the surface is zero. We want the velocity at the discharge. That's what we're trying to find. And so there we go. Crossed all that, got me this little equation right here. Um, Now HF is 4 FL over D, which is the major head loss, which is due to the main component is the uh, length of that pipe. And then you got the coefficient of expansion, coefficient of constriction, coefficient of friction, fitting of the fitting. There's no fittings, but it is an expansion and constriction. So the expansion is no, when it comes out, and the constriction and when it comes into that pipe or that fluid, whatever. All right, for steel pipes, Reynolds, and this right here actually supposed to be a G. I'm having trouble writing these equations out of the book, but as long as your units, as long as you know your units, it really doesn't too much matter. All right, for steel pipes, Reynolds numbers. For a steel pipe, for Reynolds number greater than, which is 10 to the 6, which is like very high turbulence. So if you got steel pipe with high turbulence, you can use this equation, which is straight out of the book. Um, so I plug that in, um, knowing I calculate the roughness, out of the book, and then it give me a friction factor 0.0037. Now coefficient of expansion, did this A1, A2 over A2, which is the area that which is the upstream area. A2 is the downstream area. So this tank right here, Hmm. Give me one moment. Divided by 214. So actually, you can calculate this, but we just assume that A1 is much bigger than A2. No, no, A of expansion. No, 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 no. Okay, that's wrong. That expansion goes to here, point two. So we can assume that downstream is much bigger than the upstream, and so we'll we'll have that coefficient of expansion will be 1, and coefficient of constriction downstream is much smaller than the upstream A1. Okay, so I put that 0.4 and then calculate the major head loss. 98.7. Add them together, U squared. They can be, you can put a G for if you want it in like the head form or whatever. Okay, this right here, I know I probably overdid just these units and stuff like that. It's confusing me a little bit, but I think it turned out to be the same. This right here, take that over here, 101.1. I see I add the G there, just to, just God help me. Did that. U squared, 3.59. I just made some mistakes here, so you got to square that. I don't know why I got meter cube right here. It's supposed to be meter squared per second squared. So yeah, um, this is supposed to be meters per second squared. Just ignore that. 1.89 meters per second. So that's what it's supposed to be. 1.89 meters per second after you square that. So all right, 1.89 times the cross section area 0.018, and then divided by we want it in per hour, and then came with 122 meters cube. Is in there. It's in there right there. Meters cube per hour. So there we go. I'll catch y'all in the next one. Comment below if you got any questions about this. I know I made a lot of mistakes, but we'll get this. We'll get this. We'll get through this together. All right. Bye.